So let's maybe get started with a review. So, because I like to get started with a review always of the previous class. So this diagram was the diagram that we talked a good bit about last time. And I was wondering if somebody can explain it to me. Who wants to take over teaching the class for 30 seconds? David, yeah.
So basically the idea is that if you have a certain section of your code that must be sequential, the total speed you can get from adding processors is bound pretty quickly by the fraction of the code that's sequential.
Yeah, so we talked about the fact that, like, exactly right. We talked about how, you know, we have these processors now that these computers that have tons and tons of processing elements. And today we're going to talk about some computers that have a lot of processing elements. But this graph was pointing out that for a program where a significant fraction, and by significant I don't mean really significant, I mean maybe 10% of the work it has to do is inherently sequential, then the bound on the speed up you're ever going to get is 10x. Right? So if you have to, you know, if you had a program that took 10 seconds on one core, and it fundamentally takes 1 second because of sequential stuff, even if you parallelize the other 9 seconds completely perfectly over an infinite number of processors, the code's still going to take 1 second, right? And so that's what this graph is plotting, and it's showing you that, man, even if 1% of my program is inherently sequential because of fundamental dependencies, you know, even on a big computer with 64 cores, I'm only going to be roughly, you know, what is that, like about 40x. That's the best you could possibly hope to do. Cool. Yeah, that's exactly right. Okay. And then I wanted to finish up last time because you guys, again, like everybody's talking a lot in lecture, which is great. I have no problem not finishing my lectures at all. Well, there's always another lecture to keep going on. So we had a good discussion last time. We didn't quite finish up talking a little bit about this. Remember we had this, we had a solver that we used as the running example throughout class. And we talked about 2 different ways to write that code. And so through a lot of class, we talked about a data parallel expression of that program. So for every element in a 2D grid, we're going to compute some quantity at every grid cell. And we had this reduction at the end. And just to remind everybody in the class, what was the reduction doing? Or how would you summarize the pseudocode again? While not done, do something. So what was the do something, and how do we know when we're done? Just as a reminder, just to get this all in our heads again, because we didn't talk about this for... So what was this code doing? Nobody remembers? Yeah.
Computing the average for each red cell in one diagonal.
Well, no, this wasn't computing in a diagonal, no.
Oh, that was...
Yeah, this was after we moved to the alternative formulation of the problem. So what's this code doing? Help me out. Yeah.
So this function is going to operate on the right cell after you cells.
Okay, good. So just to remind everybody, this was it was an iterative solver. It was doing a type of relaxation. And if you don't want to think about the details of the solver, the structure of the code was while not done, for all elements in the grid, perform a computation where essentially we were smoothing out the quantity on the grid. We were blurring it out. And then we were adding up how much every cell changed after every iteration. So this is the big global reduction. And if there was a lot of change, we would keep going until it converged. And if there wasn't a lot of change, we would stop. And so the way we read this code is, well, we have a sequential thread of control. At the for all, we can think about it as potentially parallel execution. And then all of that execution completes right here at the end of the block, and then again, we're running serially again. So we talked about that in the first half of class. In the second half of class, we rewrote the same code using we manually did all the communication and orchestration with locks and global variables. So remember this code, again, this is just all review, is now this is being run by every thread. Every processor is executing this code. And now every processor gets its ID. I'm processor 1, I'm thread 1, I'm thread 2, I'm thread 10. It computed a set of rows, a chunk of the array that it was responsible for. It did that work right here, remember? And then all of the workers were updating the global change, and then all of the workers independently ran this logic to say, well, if I'm not done, or if we're all together not done, we need to go back to the top of the loop, right? So there are two interesting things. Let me jump ahead. We talked about a few things here. Was that we took a lock here. So there's two interesting things in the code that I want to make sure that everybody took notice of because it started to get towards the end of the class. There's a lock here, and there's a barrier here. There's a couple of other barriers, actually. But let's talk about the lock first. Why was this lock here? Isha? Okay, so the race condition, and can you explain to me what you mean by the race condition? This is, terminology. Let's explain it.
So if one thread reads the value of diff and tries to update it, and in the meantime another thread reads the same value and tries to update it, so the two threads are reading the same value and trying to write to the same variable, but then we lose the computation, and that's the race condition.
Okay, so how do we execute a read, modify, write in a processor? We're going to do a load. We're going to load the value into a register. And I didn't print out note cards, but it would have been a nice demo here. Step one would be to load the value from memory into a register. I'm going to perform a math operation, in this case, add, to update the value. And then I'm going to write the final value back out to memory, right? Because this is a shared memory machine, and that's how other people are going to see my update. So what can go wrong if I did not make that sequence of operations atomic? What can go wrong? Yeah.
It could end up terminating too early because diff would be smaller than it should be.
It could be smaller than it should be. So let's talk through this. So let's say the value of diff is, 100. And I just computed that the change in the cell that I just was about to update is, let's say, the value 10. So I load 100 into the register. I update it. It's now 110. And I write it back out to memory. So everything seems fine. So what could have gone wrong?
Another thread could have also read 100 and let's say it got 20. It should have been 130 combining those. But
Okay, so let's say you're that other thread, right? And let's say you want to add 5. So I read 100. I update 100. I'm starting to write the value back out to memory. You read the value of diff. You get what value? 100. You update the value. I write 110 back to memory. And what did you just write? You wrote 105 to memory. And what should the value have been? 115. And so the lock is doing what in this case?
It's preventing the second thread.
It's making sure, exactly, it's making sure that the sequence of operations, the read, the update, and the write, all happens atomically. Or another way to say it, it's ensuring that only one thread, when a thread is accessing that diff variable, that access is exclusive. Exactly. So here's an interesting question. Does anybody see a potential performance problem with my implementation? Oh.
While trying to update diff, one thread will prevent all the other threads going forward. They will all wait.
All the other threads, right? So you can think about this section of code. However long it takes to take the lock, to do the update, and read out to memory, this is essentially sequential code, right? And so if I go back to my graph, that lock is actually making S bigger, right? And so it might not matter at all. It might not matter that much if maybe the amount of work I do here is huge, but actually there's only a couple of math operations there every time I take the lock. So the way I wrote this code, the sequential portion might be quite substantial. The fraction of execution time where I'm doing this compared to I'm doing the stuff that can be done in parallel might be quite substantial. So does anybody have an idea on how we could do a little better?
Instead of updating diff every iteration, everyone gets their own local updated diff, and then at the end, after they go through the for loops, then they do the lock process to add it.
Good. So you're saying that, this reduction, this sum reduction, which is what I'm doing here, is associative. So what I can do, and it's also commutative, basically, if we're not worrying about I can actually, I can compute this partial sum locally for all the elements that I'm responsible for. And then we can do the global computation maybe instead at the end. And that's exactly what I did here on the next slide. So notice that now that every thread has a local variable, my diff, That is accumulated into without a lock, and then using the lock, we only perform a few updates into the final computation, into the final global value. And we perform one update per thread. So why is there no need for a lock here in this example? We go here, just to, yeah.
We don't care, the example we had before, the other person's thread was trying to write 5 and we were trying to write 10. We don't care about their 5. All we care about is our 10 that we were trying to write.
Because this is a local copy of your variable.
Yeah.
It's not possible for someone else to write to the same. The program's not written. You know that nobody else is writing. So you don't need to insert synchronization to ensure that to be the case. Exactly. Good. Okay, so let's talk about one more thing. What is this? This isn't something we've talked about. Barrier. What does this mean? Yeah.
It will start the execution of all the threads until all of them like are done with execution up until that point. And it's done because like you don't want execution to like one part of the thread to reach the next stage and cause like some results for a change.
So locks are synchronization primitives I can use to serialize computation or ensure mutual exclusion. A barrier is a different type of synchronization primitive, and you may have talked about it in 213, I don't know actually, is that it says, look, all threads must get to this point, or at least number of processors, in this case all of them, have to get to this point before any of the threads continue on past it. So if I wanted to draw this more visually, this computation is like compute the red cells, barrier, compute the black cells, barrier, and so on and so on. It sets the computation up as a sequence of phases. So in this solver, notice that I have 3 different barriers. It's a lot of barriers. So let's talk about why I needed all of these here. So maybe this might be the easiest one to start thinking about. So why do you think this barrier is here in the code? Yeah.
If you didn't have that barrier there, maybe the diff wasn't completely updated yet, and then some thread would read the diff and be like, oh, the diff is 0, let's just finish now, and then everybody else updates it and makes the diff huge, and then maybe you weren't supposed to end quickly.
Awesome. So this barrier is here because if we're all accumulating, imagine you accumulated your contribution to the sum, and then you immediately went to check to see if we've converged. All the other threads may not have had a time to write their contributions into the sum, and you might say, oh yeah, it's time to converge, I'm going to stop, and you might make that decision prematurely. Good, so that's why that one's there. That makes a lot of sense. Why is this one here? Yeah.
It ensures that no thread will jump to its next iteration of the while loop. Like they all jump together basically.
So what? What's wrong with that? That's absolutely true. But what's wrong? Let's say I just remove this. I comment this line of code out. What happens next? Yeah.
If one of the threads sets it to true, then
Or not true, but just say we got rid of it, right? So I'm going to immediately jump up here. You're on the right track. You're totally on the right track. Okay, I'll go behind you.
So diff will again become 0.
So I'm going to just go right up ahead, and I'm going to go ahead and get ready for the next iteration of the loop. I'm going to set diff to 0, perhaps before any thread has checked to see if I've converged, and all the other threads might go, oh, we're converged. There was no change at all. And then, of course, why do I have this barrier here?
because the same reason, we're clearing out diff, and we want to make sure that every single thread has their diff 0 before another one.
Before we start incrementing into it down here as well. Good. Okay, so what we're not going to talk about here in class, and I want to take this discussion offline to the website, is I can do this. How many of these barriers do you think we can eliminate and still have a good program? Right? Because every time we have one of these barriers, everybody has to wait till everybody's done, and everybody knows in going out to a restaurant with your friends that every time you have to wait up for other people there's a loss of efficiency there. And I'm going to tell you that, the answer is right here on the next slide, but we won't look at it, but I can do it with one barrier. I can do the whole thing correctly with one barrier. And so I want to have this discussion. It's a great opportunity for making some comments on the web. The solution's obviously right there on the next slide on the web, but see if you can solve this on your own before you take a look at the next slide. Or at the very least, let's explain why the next slide works together. Okay, great. Great. So to recap from last time, we talked about 2 different ways to implement this program. And there are a lot of really cool things that happen in this program that could fit on one line of the slide. We talked about interesting optimization strategies, trying to remove locks, reduce number of barriers. We talked about, the biggest thing was we actually changed the whole algorithm from when we started to move from an algorithm that converged quickly but was not parallel to an algorithm that may not converge as well but is easy to parallelize. And you'll see a lot of modern research. This example was from a textbook, I think, written in the early 90s. But tons of research right now in machine learning and AI, they all have statistical computations at their root. And so we can trade off stability or convergence for parallelism. And there's a lot of modern algorithm development research dealing with the exact same issues that we talked about here in class. And also, we started with that Amdahl's law graph to point out how much parallelism you really, really need in order to actually make use of these big machines. So good. Okay. So assignment 2 is coming out. Assignment 2 is probably the first time many of you have programmed a graphics processor, a GPU. So this lecture is probably not in the most ideal spot in the class, but I need to give this lecture today about how GPUs work and how we program them, so you have all the tools you need to get started on assignment 2. So let's talk a little bit about that now. Has anybody actually written code for a GPU? Cool. A few people have. Great. So first of all, if you're paying attention in this class, your first reaction should be, what's the big deal at all? You told me in lecture 2 to think about a GPU as just a pile of cores, and some of them happen to have SIMD processing and threading and stuff like that. Well, I know how to write code for those. I write code for CPUs all the time. What's so different? And really, that's the right attitude to have. That's completely the right attitude to have. There's nothing that we're going to talk about today is, graphics is not going to come up at all. The fact that it's a GPU, the graphics processing unit, is there for completely other reasons that are historical. To you, it's just going to be another multi-core processor. But I thought it might be kind of interesting to tell you how we got here. So I'm going to give you a 10-minute, 15-minute version of sort of how it came to pass that these processors that basically a decade ago were being designed to play Quake well, to run Quake, now all of a sudden are at the heart of the world's 2 largest, or the number 2 supercomputer in the world. So let's talk about how we get there. So first of all, these processors, what they were originally designed to do is they were designed to be very efficient systems for making pretty pictures. And to be a little bit more precise is I'm going to give, the application will describe a scene in mathematical terms, such as it'll give me a mesh, it'll give me some description of the materials, of the lighting in the scene. And if I just run for the sort of standard equations of physics, I can compute what that particular mesh might look like under some lighting conditions. So the input is some description of a scene. The output is a picture, is an image. And that's what renderers do. And if you're a gamer, these days they do it quite well. So this is an example of, this is real time, 30 frames per second on a reasonably high-end GPU, and I don't have time. Like if you just Google kite demo on YouTube, you can see the full 2-minute demo, and it's quite impressive. You're like, that's pretty much a movie. It's getting really, really close to what we can do these days. Another example looks like this. And so you can imagine that there's a lot of calculations that need to be done to produce an image like this on a 2 megapixel or a 4 megapixel display at 60 or maybe 120 frames per second. So now I'm going to tell you how that works. And some of the things in this class that I want you to learn are not necessarily technical. One of the things that I really like students in this class to be able to do is to be able to stand up and actually explain a system. So how many people in this class have actually taken graphics? Okay, there's a fair number. How many have taken it with me? Much smaller number. Okay, so some of this you may already know, but at least over half the class has never taken a graphics course before. And I would like to see if over the next 5 minutes I can teach you how you make a picture that looks like this. Okay, so the first thing that any good systems person does when they're trying to explain a system to somebody else is they start with things. Because systems have state, they have things, and then they have operations that manipulate things. If I wanted to describe to you how a processor works, remember I said there are registers, and there's an execution unit that modifies the registers. And everybody can get in their head, well, I know what state is, I know what the value of a variable is, I know that there are things, there are nouns in the world, and I know that there are also verbs. So in the case of graphics, conveniently, one of our most important things are vertices, points in space that I can connect up to form primitives like points and lines and triangles. And so that's one of the most important entities in the system. Some vertices or some primitives and some triangles. Okay. And every picture that's ever been made by a GPU is basically just operations on only 4 things. One of the reasons why these systems have been so successful is that they've boiled it down to 4 simple ideas. We have vertices that we're going to group together into primitives, like triangles. For every triangle, we're going to divide that sort of into small pieces that correspond to pixels. And then we're just going to, those are actually called fragments. And if I put all those fragments into an image at the right spot, I get the value and color of pixels. So those are some things. Everybody kind of knows what a vertex might be in 3D space. Everybody knows what a triangle is. Everybody knows what a pixel is. And the fragment is a little bit the only concept that's not immediately obvious. But you can imagine breaking that triangle up into a lot of little pieces, computing the color of those pieces, and then sticking them into an image. So those are our nouns. Here are our verbs. So I need some operations that create and manipulate these things, right? And so let's just walk through how we do that. So I told you we needed some vertices. And so the first thing is maybe the application provides the system with a list of vertex positions. So I have vertex 0 is XYZ, vertex 1 is XYZ, vertex 2 is XYZ, and so on and so on. And I can interpret this list of vertices. We could just say that I'll implicitly say that every 3 vertices corresponds to a triangle. So you can interpret this list of 4 vertices as defining 2 triangles. The first triangle is vertex 0, 1, 2. The next triangle is vertex 1, 2, 3. Does that make sense? So that's the input. And you'll notice that I'm kind of summarizing the whole thing on the right here. The input is just the buffer of vertex positions. And now I just have a list of these vertices. So operation 1 is given these vertices in 3D space, I can compute, and I'm not going to tell you how to compute, that's a graphics class, but I can compute where those vertices fall on screen if I gave you a position of the camera. That makes sense, right? You can imagine that that can be done. So now I have an input buffer of vertices. I create a list of these vertices, and for every one of them, I'm going to apply a kernel to them, and that kernel for every vertex just computes a 2D coordinate where on screen it's going to lie. Simple thing. And you can notice that these collections of input 3D vertices and output 2D vertices, I'm calling streams here in the figure. Then I'm going to take these vertices on screen and I'm going to group them together into triangles. Not a particularly hard operation. I showed you how to do that one already, right? So now we have a stream of vertices, and I have an operation that groups them into triangles, or other primitives, but in this case, triangles. Everybody still following me? Okay. And then you can imagine that now that I know where these triangles are on screen, I'm going to have an operation that cuts a triangle up into a bunch of fragments. And I'm going to compute one fragment for every pixel on screen a triangle overlaps. So in this particular case, I have these 2 triangles, and let's say T0 generates these fragments, and T1 generates these fragments. So going back to our diagram, for all vertices, compute their projection on the screen to produce a new collection of 2D vertices. For that collection, group them by 3 into triangles. For every triangle, split it up into these fragments. For every fragment, compute its color. Using a whole bunch of advanced physics to compute how much light bounces off the triangle at that position and this and that. But basically, I'm just computing its color. And then I'm going to take all of these pieces of the triangle, and I'm going to stick them together in the final output image. So all of computer graphics and everything that a GPU is designed to do was perform these operations, 1, 2, 3, 4, 5, 6, on streams or large collections of only 4 types of entities, 4 types of things. So does this look very similar to something you've seen before in this class? This computational structure. Doesn't look very similar, doesn't look very familiar? If I completely got rid of this side of the screen and just showed you this, does it remind you of any way to think about parallel programming? Yeah. Or you could think about it with barriers as one possible implementation. Yeah, actually you could. I see that connection. In the subtasks, yes. Anything else? I mean, it's just a pure streaming data parallel way of thinking about making a picture. Completely, right? And so one of the interesting things is that the early people in graphics figured this out and were able to say, look, here are the right representations for making pictures, and that's often called the graphics pipeline, which is this sequence of operations on those collections of things. Okay. Now, to make those pictures that I showed you at the very beginning of class, I mean, there was amazing lighting and shadows, is that, you know, like we really need to get into, well, how the heck do we compute the color of a fragment and things like that. And, you know, one example would be if you look around this room, look at the clothing everybody's wearing, the surfaces on the walls, on the floor. There's a lot of different materials in the world. A lot of different materials in the world. And if you want to make realistic pictures, you need to represent those materials fairly accurately. And the early days of OpenGL, the only way that you could specify what materials were was that the API, these graphics programming systems, they gave you a few hooks to say, okay, I want you to set the parameters of the material like color or shininess or whatever. Or I want you to set the brightness of the light and the direction of the light and so on and so on. They give you a few limited ways to describe materials. But people really quickly, once we got into advanced graphics, were like, gosh, if I wanted to make all these different materials, it's pretty hard to parameterize that space. Or if I wanted to make all of these different materials, it's really hard to parameterize that space. Like the glints here versus the translucency of marble versus the reflection and so on and so on. And so the world quickly came to the conclusion that 2 of these parts of the graphics pipeline needed to be basically programmable. We're going to define how to compute the color of a fragment, how a surface looks at a pixel, by writing code. We're not just going to say it's red and green and really shiny. We're just going to write code. And so any modern GPU from the last decade or so has allowed the user to provide a piece of code which defines for every fragment how to compute its color, and also actually for some other reasons for every vertex sort of how to compute where it ends up. Because it's more than just projecting it on screen, it's animation and a lot of other things as well. Okay. And this doesn't really matter that much, but here's exactly what one of those pieces of code look like. This is like a kernel in a data parallel system. I'm going to run this function for every element that comes through. And this function will take as input, for example, some texture coordinates if you've been in graphics, or the orientation of the surface, its normal, and those will be different for every single fragment, hence the keyword varying. And it might take other parameters that are the same for every single fragment, like the light direction or a texture map or something like that. And that's why they're marked as uniform. And in fact, the ISPC uniform keyword actually came from this usage in graphics. So if I apply this function, if I map this function onto every fragment that comes through the system, I get a color, and maybe I might make a picture that looks like this, or something like that. Right? So okay, so that's where we were. We were writing code. We were like, everybody that was making a game was writing, structuring their code as here's the kernel, it's going to get mapped onto every fragment that comes by. And so back in, in the early 2000s, people were kind of looking at curves like this that we had on day 1 of the class, and you're like, man, CPUs aren't getting any faster. But these GPUs are just adding cores and adding cores and adding cores. Some folks were like, wouldn't it be kind of interesting if we could start using these graphics processors that we can kind of write code for to do something fairly useful, to do something more useful than just make games. And so people started to hack. And they really started to hack. They were like, you know what? This sounds a whole lot like data parallelism that Guy Blellock and the MIT guys were doing on the connection machine back in the 80s. So how about we just draw 2 triangles that cover the entire screen, which means there'll be a fragment generated for every pixel on screen. And if I set my screen size to be the same size as the output arrays, I now have a processor that will generate one element, will map a kernel function that I give it onto elements of a stream, and there happen to be the same number of elements as the size of the screen. Completely hacky. Completely. And some folks, some enterprising grad students at UNC and at Caltech started doing some very interesting things by basically hacking what you could do with graphics cards. So they did things like fluid simulation or ray tracing and various types of heat diffusion simulations, anything that could be basically structured as map this simple kernel onto this array of values. And in fact, some other enterprising grad students in the graphics lab at Stanford said, okay, this hacking's really stupid. We're a little bit more familiar with compilers and the history of data parallelism. How about we write a compiler where you write your kernel and your streams, and this is the syntax that I borrowed from earlier in the class, and hey, let's just map the kernel onto the stream, and let's compile this down to the appropriate OpenGL graphics calls to do that. This got compiled into draw the 2 triangles, set your fragment shader to this, and so on, which was also really hacky, but not quite as hacky. Okay. So that was, I think, roughly in 2004. And then enough people were starting to do this, and people were like, wow, we can actually do a few things really efficiently on these GPUs. And that's when the industry got involved and said, okay, let's clean this whole thing up a little bit and start acting like a real processor to some extent. So there is another mode that you can run any GPU in today. This is what you'll use in the class, where you don't think about the GPU as implementing this pipeline of graphics operations. You think about this GPU basically as a big data parallel processor. And that's how we're going to use it in this class. So just to be really clear, if I wanted to run some code on the CPU, and for those of you that have taken 410, you have done this. If you want to get a thread running on a CPU, what do? Is you load the program binary into memory, you trap, you basically you interrupt the processor, you set up an execution context by setting up the registers, the program counter, the memory mappings, and whatever, and you say go. Run this particular program within this execution context. The operating system is responsible for giving a thread an execution context to run in on the processor. If you wanted to run code on a graphics processor, and the graphics processor, you think about it as an implementation of the graphics pipeline, what you would do as an application is you would hand the GPU, here is my fragment kernel, here's my one little function for the fragment processing and for vertex processing. And you would say, here's a buffer of vertices, go. You don't think about threads, you don't think about execution context or cores. The only interface to the hardware was, here's the kernel, here's a list of vertices and some extra camera parameters and whatnot, go. This was the ISA. There's nothing else. You could not use the GPU to do anything else but this. So what we're going to talk about today is what an alternative ISA, or an alternative interface to the GPU hardware, which is nothing like graphics and not quite like a normal CPU. What we're going to do now is we're going to say, hey, here's my kernel function. Run it n times. So I'm going to put some buffers in memory for you that you can read and write from. Here's my kernel function. Run it n times. It'd be like almost like the operating system telling a CPU, hey, here's a program binary, run it 1,000 times with different values of thread number or something like that. So it's the data parallelism is actually at the hardware level. So does that make sense? Like the only thing you can do is say, here's a kernel, here's a program binary, I want you to run it n times. Make sense? And in fact, this interface is actually far simpler than this one. Because this is like, here's a list of vertices, transform them, rasterize them, generate these fragments, do all this other graphic stuff that's not written into your program at all. You get a lot for free. In compute mode, it's, here's my binary, I want you to run it n times. Okay? And the programming language you're going to use in assignment 2, the CUDA programming language, is the language in which you use to specify your kernel function, the function that you're going to map onto some collection. And it was it was introduced in 2007. It was done by the PhD student that actually did that original Brook compiler, the hackiness to get this stuff onto GPUs. He took his dissertation, went immediately to NVIDIA, and they gave him free rein to sort of design a programming language around this. Many of you might have heard of a system called OpenCL. OpenCL is the open standards version of CUDA. CUDA only runs on NVIDIA GPUs. In this class, I will teach you and have you write in CUDA and not OpenCL because it's just a little bit easier to use and better documented. So you'll be happier using CUDA, even though everything we say in this class conceptually has a one-to-one mapping into OpenCL, which means you could run these programs on Intel or AMD or other GPUs out there in the world as well. Yes?
What kind of differences are there between CUDA and OpenCL?
I mean, there are plenty of differences, but for, at a 1,000-foot level, none.
The language is practically the
Yeah,
same.
yeah, you could search and replace keywords and basically be the same. Yes. The designers of OpenGL would not agree with that statement, but they're more or less wrong. They're more or less wrong. Okay, so let's talk about things a little bit. So we're going to talk a little bit, of course, we're going to start with abstractions. We're going to start with the semantics of the programming language. And then we're going to talk about how it is implemented on modern GPUs. And then we'll go into some more detail about, hey, just for fun, let's learn a little bit more about GPU architecture just to make sure we understand what's going on. Okay, so are there any questions? Are we good? Because I need to clarify something again, unfortunately. This is a sign of the state of the art in our field, where I'm going to use thread today to mean something completely different than I did in every other lecture so far. Okay. So in this lecture, in the same way that when I talked about ISPC, I tried to use ISPC's terminology in terms of program instances and things like that. Today, when I use the term thread, I'm going to be talking in CUDA terminology. So the CUDA programming language ascribes a particular semantics to a CUDA thread, and if I say thread, that's what I mean, or I hope that's what I mean. You will find, and you should conclude, that when you think about a P thread on a CPU and you think about a CUDA thread running on a GPU, they're not one-to-one with each other at all. And so I'd like you to tell me at the end of this lecture what you think the correspondence is. Okay, so let's get started. So the first thing to note is I said, okay, we're going to run this kernel n times. N is a little bit more complicated than that for sort of some historical reasons, but also for some convenience reasons. So you don't just say, I'm going to run a kernel n times. CUDA has a model of a hierarchical set of simultaneously running CUDA threads. And what I mean by that is, let's say we had some kernel called matrix add, and I'm not going to tell you what that does right now. It's just going to add two 2D matrices. And this is saying I want you to run that kernel on these arguments, A, B, and C. A, B, and C are just normal C arrays. And I want you to do it over this many blocks with this many threads per block. So you can think about this right here as just the number n, except we're not going to specify it as a 1D number. We're going to specify it as a multi-dimensional number, because it can be convenient for things like image processing and ND array codes, which GPUs are particularly helpful for. So that code right there says, we're going to launch this kernel. We're going to map this kernel. And we're going to run it in terms of, in groups of 12 threads each. That's threads per block. And we're going to run 72 blocks of it. Or sorry, not 72, 6 blocks of it. So that's going to launch the kernel matrix add, which I haven't shown you yet, 72 times. And those launches are going to be organized in terms of, what did I get this? 4 by 3 set of threads here. And then we're going to do 12 of these blocks. So it's just like we have a multi-dimensional thread ID. That's the only thing here. It's a little bit messy, but that's the way the system is designed to work. Is this okay? Nobody's too confused by this here. Okay. So now let me show you what the kernel looks like. CUDA is designed to look just like C code. So the kernel function takes as input the C-style arrays, A, B, and C. It uses its thread index in the block and the index of the block in the overall launch to compute a unique thread ID, in this case, I and J. And then every single CUDA thread will perform this computation. So a CUDA thread should have a mapping in your head to an ISPC program instance. But instead of program index, it's just a little bit more complicated to compute where you are. And the reason why they do that, just for historical purposes, is that they can give you a 2D number, and if you wanted, it's easier to convert a 2 or 3D number to a linear offset than it is to do a division to go the other direction. So they do that for performance reasons. So it's not a particularly important detail at all. So this code here says we're going to run matrix add. We're going to launch a bunch of CUDA threads. We're going to organize them into 4x3 thread blocks, and we're going to launch 12 of those blocks. 6 of those blocks. Sorry, 6 of those blocks. And that every one of those threads is going to run this code. So if this is seems like ISPC, that's absolutely correct. In fact, it went the other way as this existed, and then the ISPC guys used these ideas for CPU programming as well. Okay. And yes, good. So this code here is your normal C program running on the CPU with a little bit of syntactic sugar to say, launch the matrix add kernel this many times. Here is the kernel that runs for every single one of those threads. So just to repeat that one more time, that red line at the top creates 72 CUDA threads. Yes?
It creates these 72 CUDA threads because my matrix has 72 elements in it? Is that the reason?
Well, I've done that myself. No, it creates 72 threads because I told it to. I told it to create 6 blocks. That's num blocks. And every block needs to have 12 threads in it. But
that's you, because of your domain knowledge of the size of the matrix, you calculated those and then gave it.
I wrote all those code, yes. So that is a great question in that CUDA runs the number of threads that I tell it to. CUDA does not map the kernel onto a collection officially. I told it to create 1 thread per element, but that was my choice as a programmer, which is slightly different, right?
So could you have given it...
I could have told CUDA to create 1 billion threads, and it would have created 1 billion threads. I could have told CUDA to create 1 thread, and it would have created 1.
Is there such a struct like for all for this where you
No.
Do like an iteration where each
No,
of them...
there is only launching threads. It's trying to be very, very C-like in some way. Exactly. Okay. So this code on the top is running on the CPU. This code on the bottom will run many times on the GPU. Right? And to answer your question here, imagine that I had a thread block size of 4 by 3. See the threads per block. But I had an array that wasn't evenly divisible by 4 by 3, such as 11 by 5. Notice that I've added logic to my code to say, hey, look, every thread takes 1 element of the input array, and some of those threads do nothing because they would have accessed out of bounds. So this is meant to be a parallel version of low-level C. This is not meant to be mapping a kernel onto a collection. Yes?
Do you choose your block size and grid size based on the hardware, or?
There'll be a lot of factors that go into that, and we'll talk more about it later. But just for now, let's everybody keep in mind that we have a kernel, and for whatever reason, which I'll tell you in a second, CUDA decides to group a bunch of threads into a block, and then it can create many blocks. Okay. So the execution model in your head right now should be, well, I have a normal CPU, I have a regular CPU, and it's running an application, and I have a GPU, which is often called a CUDA device, and that the CUDA code will run over here. The regular host application will run on your traditional CPU over here. And that both the CPU has its address space in the process that you're running, and the GPU has a different address space. And so if I want to move data over to the GPU, I have to get it over there. And so you have the ability to allocate data on the GPU as well as move data over there. So let's take a look at this code. Look, it's a CUDA malloc. So this is malloc data in that address space. And we can execute a memcopy from a local pointer right here, A, to device A of this many bytes. And that will be a transfer from your processor's address space on the CPU to the memory that's over there off by the GPU. So if you bought like a high-end GPU card for gaming, you'll notice it has a bunch of DRAM on it. That's the memory that I'm talking about over there. Okay. Does CUDA memcopy remind you of something? This is actually kind of interesting, right? Because memcopy in a process is just moving data from one address, some buffer in the same address space to another spot in the same address space. This is actually quite different. So if we call CUDA malloc device A, this is a pointer here into the GPU process's address space. And if you try and dereference it, which I don't here, if you try and dereference that pointer, you're going to get junk. In fact, you will segfault. Because this is not a pointer into to the local address space of the CPU process. So this CUDA memcopy should actually remind you a lot more of a message send than actually any kind of memory copy within the same address space. It's almost like we're sending this buffer over to the GPU, and a memcopy back will bring that buffer back over. So it's a message passing analogy is much, much better here. Okay. So yeah, so this lecture is going to push you a little bit because it's taking every concept we've taken now and just kind of applying it over and over in a bunch of different contexts. And just to finish up the abstractions for you is that we have, when I launch some threads, CUDA gives you the ability for every thread to have its own private address space. You're used to that, thread local variables. It has the ability to have an address space that's global to all threads, shared memory, global memory. So that's just like a normal shared address space. And then there's an additional address space that is shared only among threads in a block. And so now you're starting to see, well, why the heck did they put all this cruft in there? Remember, this is a language that's designed to be fast. It's not designed to be particularly elegant. So threads that are placed in the same block can communicate via this shared address space. And what's in your head as a programmer is, since that shared address space is limited only to a small number of threads, perhaps it can be implemented much, much more efficiently or faster than communication out to the global memory system and back. Okay, so that's what should be kind of in your head right now, is they have put a stake in the ground which says we're going to give you per thread memory shared by everybody, and memory shared only by the threads in a block. So that might dictate your choice of block size a little bit by saying, oh, how many threads do I need to cooperate on the same thing? Question.
The only reason for having blocks is the block shared memory, or what's the point of having blocks?
That's about it. It's just a region where you're declaring, hey, I want some locality here. These threads are going to do work, and they're going to exchange some data. So it's a big hint to the CUDA system to say, you probably want to put these maybe on the same core or close to each other somehow. So they've said that we want that hint, and so they've baked it into the semantics of the programming model. So if you never ever communicate, you would never use that shared memory. Like if you go back to my example here, every thread just processes one element of the input. I don't even think about that shared memory system.
So then we could have done like one block and 72 threads.
If you wanted to, it would have been a valid program to get the same result.
What about having 72 blocks and one thread per block?
So same result. Very different performance characteristics, and we'll talk about them in a second. Yeah. like anything else in this class, right? So this this example might make some of these differences a little bit more clear. So imagine we're going to write this program. And this program is going to perform a convolution on, just to make it simple, a 1D array. So this is actually very much like the grid solver in a sense, right? Is that every output element is just the average of the 3 elements right next to it. And if I did this in 2 dimensions, it would be an image blur. But I'll just do it in 1 dimension because it's a much easier picture to draw. So let's write this in CUDA. So let's start down here. This is the top level stuff. So we allocate the input array and the output array. Here I decided to make that array 1,000,000 elements in size. And then we're going to call our kernel, which is called convolve. And I chose, and I'm not going to tell you why just yet, but I happen to, let's just say, 128 threads in a block. And then how many blocks do I need? Well, it needs to be n over threads per block, and let's just assume everything divides equally for now, just to keep the slide simple. So you can see how I'm basically launching 1 thread here for every output element of the array. Even though the code isn't mapped this kernel onto this array, I've essentially done that here. We're going to map the kernel onto every output element. And then if we look at the kernel, it's exactly what you might think. There's a little bit of messiness to compute the threads index in 1D from the block index and the thread index and so on and so on. And then every thread will load the appropriate values. Oops, this should be plus I, excuse me. I'll fix that. Every thread should load the appropriate values. Let me just fix it real quick so I don't confuse anybody. Oh no. There we go. Loads the appropriate values and then writes the result out. Right? So does this make sense? Good. So every thread here performs 3 loads, 3 additions, and 1 store. Let me write a slightly more efficient CUDA program, which is even more efficient today. So here's another version of a program that does the exact same thing, and I'm going to leverage this shared memory. So now I still have a kernel. Oh, this is all the same. I have a little bit more complicated kernel now. And the kernel is still running in this form of 128 threads per block. And now I've allocated a shared memory allocation. See, shared float support threads per block, plus 2. So I've allocated 130 elements in shared memory. And there's one of these allocations per block. Not per thread, but per block. So it's a 520 byte allocation, 130 times 4. And then every thread here, now remember, 128 threads in the block are running this code. And to compute the 128 outputs, we need 130 inputs. Does that make sense? And notice that there's 130 slots in that shared memory. So all the threads end up, what they do is they load, every one of them loads 1 value from memory and puts it in that shared memory buffer. So 128 threads issue a load and put 128 values into the shared buffer. And then 2 of them, if thread index is less than 2, 2 of them end up putting the 129th and the 130th value into the buffer. And then every thread, instead of accessing main memory, accesses the shared buffer to compute the convolution that it needs. It just pulls the data out of the shared buffer. And notice that I have this command called sync threads, which should be just called block barrier, which is a barrier for all the threads in the block and not a barrier across all the threads in the machine. So this code is all the threads in a block cooperatively load the data that's necessary. They stick it in shared memory. They wait until everybody has agreed that they've all done their part of the job. And then they use the shared memory to perform the convolution. And the reasons why this is a slightly better program in a CUDA world is that shared memory you should think of as almost like an L1 cache. It's really, really, really fast. And moreover, if you actually think about how many instructions were executed, here we only executed 130 load instructions across the whole block. Whereas before, we executed 3 times 128 load instructions. So even though on a CPU, many of those loads might have hit the cache, that cache is, first of all, going to be slower than how a GPU implements this shared memory. And second of all, it actually took the instruction issue slots. And so we actually reduced the number of instructions by a factor of 3. So we're getting a little bit complicated on why we're using shared memory, but that's the actual reason. So does everybody understand? Can you talk through yourself what this code is doing? So the way to think about a CUDA program is to think about what's going on in a block, not to think about what all the threads are doing. You can think about CUDA as launching a bunch of blocks, and every block is executed by a number of threads. That's the way I like to think about it. And there are a number of synchronization primitives you have at your disposal, like the sync threads, which is a barrier for all the threads in a block. There are atomic operations to synchronize the threads. And then there's a bunch of CPU, GPU synchronization. But you guys can look all that up in the documentation.
Is the shared memory the scratch pad?
The shared memory is a scratch pad, yes. It is implemented. It will be implemented, even though that's not in the semantics of the program. CUDA just says, look, there's an extra address space that you can read and write to. The point is that address space is always backed by really fast scratch pad memory right next to the execution units, yes. Okay. Right. So our abstractions are lots of threads. We organize the threads into a hierarchy, into blocks, and then a launch creates a bunch of blocks. And that there are 2 address spaces. There's code running on the CPU within the address space of the process. There are threads running on the GPU. Each thread runs within its own address space. They can share variables through a per block address space, or they can share variables through a GPU-only address space. That's what exists, yes?
You mentioned about saying 3 times of the instructions. Where does this 3 times come from?
Where did it come
What is
from? Okay,
compared to?
so let's compare the 2 programs. So here, remember this is SPMD code, so every thread is running this code. Make sense? So every thread issues load, 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 load. Three iterations of this loop. Oh, I see where I'm confusing you, actually. Okay. So there's 3 loads out to memory. And another way you can think about it is there are 3 memory transactions actually hitting the memory controller, or at least hitting the cache controller in this case. In this case, nope. Oh, sorry. I meant to be pointing to that one. Does that make sense? Yeah, okay. So in this case, every thread only loads data once. And only 2 of them have to actually keep going because the 130 doesn't divide 128 equally. So you're doing a lot more low-level programming to eliminate the extra memory transactions that on a CPU, a really nice cache might absorb. Okay. So here's a question for you. Here's this convolution code, nothing new, same code. And remember we said we're going to run it on an array of 1 million elements. So this launch here technically says launch over 1 million CUDA threads. And what happens if I did that on a CPU and I said launch over 1 million P threads all at once? I showed you in that code last time that the difference between launching a ton of P threads versus spawning up just some workers and sharing the data across the workers is like 10,000x difference in how fast the code ran. So, and also, that's like saying, let's create 1 million threads, let's create 8,000 thread blocks, which is what this is saying, and that means we need 8,000 allocations of the shared memory region. So do you think that the implementation of these semantics is the same as how maybe a pthread library or an operating system handles its threads? Apparently not, because I'm strongly hinting at it. So how might you implement this? I want to create 1 million CUDA threads. So let's, we had a big discussion about this a little bit last time. How would you implement this thing?
Can I still utilize the SIMD or hyper-threading things?
Okay. But we certainly don't have, even with how wide one of these GPUs, we don't have 1 million execution units on the chip.
Yeah, that's why
We're going to be in trouble, right?
Yeah, that's
We would
why
like to have that many.
Like,
No, go, one second.
yeah, like hyper-threading, or we just do some threads first and then.
We'll do some threads first, maybe some other. Okay, that's what we're going to have to somehow stage this, yes.
Wait, how many kind of queue do we have? Do we have like one combined queue?
Well, you know what this line of code means now. You know it means run this kernel and create 8,000 thread blocks, each of which with 128 threads. That's all it means. That's all it means. So I'm asking you, I'd like you to implement this somehow.
Doesn't the GPU have a dynamic thread allocator?
Okay, but let's not think about GPU details. Like just like at a really high level, how would you?
Like the worker threads method?
Okay, so let's elaborate on that. Yeah.
It could be similar to how tasks are implemented in that you create a number of threads that would actually be useful and then have a queue of work to give threads once whatever was done before is finished.
Okay, very cool. So you're saying that even though I'm creating like 1 million things to do, maybe I can just do as many as I can at once, and then we're done. That are done, I'll do some more, and so on and so on. And yes, that's exactly how we're going to go about this, which is particularly important because I'd like this program to run on a multi-core processor with 16 cores, or a cheaper GPU with 6 cores, or maybe even a GPU with 1 core, or maybe, for that matter, a CPU if I ever wanted to make a CUDA implementation for the CPU. I don't know. One thing that you should notice in the program is I never in the program put number of cores. I only put the number of threads that I wanted to create or the number of thread blocks that I wanted to have. So let's think through this a little bit. So here again, same program, nothing new. And if we compile the program, we're going to compile a binary, but the compiler is going to make sure with that binary we have a little bit of useful information. We know that this kernel can only be run with 128 CUDA threads per block. It needs 130 floats, 520 bytes of shared memory allocation. That's how much it's going to allocate. And it probably needs some number of bytes, B, I don't care for now, of local storage per thread. So the compiler statically knows most of this information. And if the program creates 8,000 thread blocks, the GPU, remember the interface to the hardware is actually run this code and run this many blocks of it with this many threads per block. So that worker pool and the scheduler, the management of that worker pool, is actually in the chip. It's actually a piece of silicon which says, oh, look, the program told me to run 8,000 thread blocks. I have 4 cores, so I will start running those programs on my cores.
Is there any way to synchronize it across blocks then?
No, because I know what you're thinking of, and we'll get to that later. Yeah. There's a big reason. The answer to the question was, can you synchronize across blocks? And the real answer is sometimes. But in general, no. Because the whole point here is we would love to be able, we need the ability to be able to run the blocks in any order we choose. Otherwise, we cannot implement the scheduler that it's going to work for any number of cores. Right? So that is that major assumption that you're starting to point out, is that thread blocks better be able to be carried out in any execution order. There better not be strong dependencies between them. Otherwise, the scheduler, which is free to make any decision it likes, it might make a decision that violates the execution order in the program. Mm-hmm. What do you mean by hard deadlines? Specifically in this case, what do you mean by that? There is certainly no implementation of any modern GPU scheduler that I'm aware of, or really any too many CPUs, hardware schedulers that I'm aware of, that make any of those real-time guarantees. One thing that will certainly happen, and I'll get to this in a second, is we're not going to oversubscribe the chip. You should think about this as now every one of these cores is a worker, and if it's doing something, I'm going to give it one job, and when it's done with that job, I'll give it another job. So you're not going to have a lot of interference between these things. To be real time, I would make my kernel small enough so I know every thread block got done in a short enough amount of time. Yeah. Okay. And so you guys are exactly right when somebody said this sounds a lot like tasks. This is yet another example in this class of this standard paradigm of when you have a lot of work to do and it's independent, The right way to do that is to create a bunch of workers using whatever means you have and start spawning, handing off work to those workers, sharing resources across all these calls. We saw that in ISPC's launching tasks. You probably did that with your thread pool in 2.13 in your proxy. And you'll see it again over and over in this class, is that as long as there's independent things to do, let's not take the overhead of allocating new resources and booting up new workers for every single one of them. Okay. So now, things get a little interesting. So I almost crashed PowerPoint trying to draw this diagram last night to describe the execution resources in every single one of these cores. Now this diagram might be a little daunting, but there's actually nothing new on here compared to what you've seen in this class. So this is one core, in NVIDIA terminology, one SMM of the modern Maxwell architecture, which was the 2014 launch. And things should be pretty familiar to you. First of all, we have 96 kilobytes of right-on-core storage to hold data that you allocate in shared memory. Super high bandwidth, super low latency to that memory. We have a bunch of SIMD ALUs. And in fact, we have 4 groups of 32 SIMD ALUs. We have the ability to keep on the chip, depending on how we want to count, 64 what NVIDIA calls warps. So now we need to get a little bit to break this down. So there are 64 simultaneous instruction streams. Each of those instruction streams is going to run 32 wide instructions, and only 32 wide instructions. So the chip is pretty simple. I have 64 instruction strings to choose from. Every clock, I have the ability to select 4 of the 64 and run them. And I have the ability to actually do ILP within each of those instruction streams, so I can dispatch up to 2 instructions from any one instruction stream per clock. So best case scenario, I can find 8 runnable warps, which I would almost want to call Intel-style threads, like normal execution contexts, instruction streams. I'll pick 4 of them. I'll try and find 2 instructions in each of those. And I can run up to 4 32-wide SIMD instructions per clock. If you're concerned about the 8 versus 4 here, I'm not showing you the load store units and some extra math. So there's some other execution units that can do some other stuff as well. So in terms of lecture 2, what is this? This is a core, 64-way multi-threading in terms of lecture 2, 32-wide SIMD, 2-wide ILP within a thread, and actually simultaneous multi-threading in which we can run up to 4 warps at the same time. Nothing new here, just being pushed to a much larger degree than what you see on an Intel processor. Okay, so if we go back to our kernel on the right, I've kind of basically summarized this slide already, is that CUDA executes kernels as SPMD programs. Groups of 32 CUDA threads are mapped to these 32-wide SIMD instructions in the same way that an ISPC gang is mapped to SIMD instructions on a CPU. So a convolved thread block, which used 128 CUDA threads, is executed on the hardware in terms of 4 of these instruction streams called warps. That's where you get the 4 times 32, 128 CUDA threads per block. So this particular core can actually run up to 16 thread blocks at once, right? Because every thread block needs 4 warps, and I have 64 interleaved warps that I can keep track of on this chip. Okay? So to review, every clock select up to 4 runnable instruction streams, 4 runnable warps, try and grab 2 independent instructions from those warps, and figure out if any of those SIMD multiply add units can actually execute the instructions. Nothing different from lecture 2. And of course, a modern, like a GTX 980 has 16 of these connected up to a 2 megabyte L2 cache and a DDR5. So it's pretty wide, pretty fast memory bus, 224 gigabytes per second. And if you do the math, things get kind of crazy, right? So 1 second, you show. So we're at 1.1 gigahertz clock. We have 16 of these things per chip. Every one of these has 64 warps times 32. That's 2,000 CUDA threads per block per SM, per core. 16 cores, that is at peak latency hiding ability, that's 32,000 CUDA threads per chip. So if you're not running, my array size of 1,000,000 is big enough, but not that much bigger than the width of the chip. So you better be running, the smallest vector that you give this thing better be at least some multiple, some non-trivial multiple of 32,000, or it basically is just not going to get going at all. And in fact, that's at a TDP of 165 watts. Okay? Isha, you had a question.
Yeah, why are there so many fetch and decode units when there are only like 4 blocks of 30?
Right, so that was one thing, that's a good observation. One thing I didn't draw on this thing, because it would just kind of complicate the story a little bit, is remember there's other stuff around here. There are other types of instructions that aren't just arithmetic. There's like on a GPU, there's special things for POW, X, sine, cosine, that kind of stuff. There's also load and store units. There might even be some like integer math these days. And so there's compute resources that I'm not even putting on here that some of those instruction issue slots can fill. Okay, so let's see if we understand what's going on. So let's run a kernel, but we're not going to run it on that massive thing because I'm just not going to draw that. Let's run it on a much smaller low-end GPU, which happens to have 2 of these cores. It has storage for 12 warps instead of 64. And let's just say it has 1.5 kilobytes of shared memory rather than, well, what did I say, 96. Because we can actually work through this experiment, not that other one, because that would be insane. Okay, so let's say that we're going to run this convolve program on this thing. So we hand the chip a command which says run convolve and run this many thread blocks of it. Let's say 1,000 thread blocks, just to keep the numbers easy. So that's the command I hand the GPU. I hand it program text, I hand it the binary, and I say, well, there's some metadata about the binary, meaning that it needs, 512 bytes of shared memory, it needs 128 threads per block, and I want you to run 1,000 blocks. Make sense? What do you think the chip's going to do now? There's something real, there's some logic here, which is hardwired into the chip. We have a scheduler. Let's be that scheduler. What do you think the chip's going to do? Let's come up with an algorithm for running this, scheduling this program onto the machine. You want to get it started?
Well, firstly, it's going to put a block on each of the 2 cores.
Okay, well, let's take one baby step. What's the first thing you're going to do?
It's going to take the first block and put it on the first core.
Okay, and how does it get the core ready?
Does it get it ready?
Yeah.
It starts reading instructions.
Sorry, yeah, that wasn't very clear. Here, I'll just help you out. So if I'm going to do that, so I'm going to, first of all, I need to reserve the execution context. I need to say, look, there's 12 execution contexts. I'm going to grab the first the first 4 of them, or if I think about the execution context being CUDA threads, I'm going to grab the first 128. I'm going to make sure that I have room in shared memory to make a 512 byte allocation. Now, once I reserve those resources, boom, I can go. Right, so now, and then notice that I've updated my counter and my state of my scheduler to say, okay, I've actually launched one of those. And then you're right, I can continue. Same thing. Because I'm not dumb, because I'm smart, I'm going to make sure that my next block goes over here. Could I have put the next block over here? I could have. But why didn't I decide not to as a scheduler? Say it again? Oh, I have tons of context. Look, I have 12 available here, or I have 384 CUDA threads worth of context. I've only used 128. Yeah, so why would we share the execution resources of this core? We should use all the execution resources that we have. Exactly. We actually worked through a version of this on CPUs a couple classes ago. And so I'm just going to keep filling the chip up, right? So I put blocks 3 and 4, or blocks 2 and 3 on. Now I have some more, and then I think I'm done, right? Yeah, so I can't put a 3rd block on this core because I actually have the execution context. I ran out of room in shared memory, actually, because if I would have exceeded 1.5K if I would have put a 3rd one here. So the scheduler just stops at this point. I have no more workers, I have no more resources to start doing more stuff. So the cores are just running these CUDA threads now. Things are just running. And at some point, thread block 0 completes on core 0. Note its resources are free. So what does the scheduler do at this point? Just says, okay, next piece of work needs to get done. Let's put it on a core so it can get going. Boom, and I do that. Let's say that for some reason, thread block 2 completes on core 0. Thread block 1 still running. What does the scheduler do? So block 5, but thread block 1's not done.
All of them can be executed independently.
Yeah, it doesn't matter, right? Like, it does not matter what order things I start or complete, right? So let's get it on the processor so it gets going. And this is just going to continue, right, until next equals 1,000, and then we're done, and control will return to the host, to the host processor at that point. So this is your standard work queue that we've talked about several times now, except it's only being executed by, like maybe a few transistors in hardware, so that communication between the CPU and the driver and the GPU doesn't have to happen all the time. Any other? Okay, so another review question. Oh gosh. What is a warp? What is this weird terminology in GPU land called a warp? And if you never call it a warp, I could care less because I think it's a weird term. What is a warp? Well, I know what the slide said because I made it, but what do you think it is? Okay. Yeah. Yeah, I mean, you can think about it in many ways. If you want to make the CPU analogy, a warp is similar, very, very similar to a CPU-style execution context running SIMD instructions, 32-wide SIMD instructions. If you want to think about it the way the GPU people think about it, it's actually 32 completely independent execution contexts that happen to share the same instruction stream. They're religious about calling it that way. There's really not that much of a difference unless you get into the microarchitectural details. So it would be very fine in this class to say a warp is one-to-one with an execution context on an x86 processor. It happens to be 32 wide. Good, right? So a warp is an implementation detail of how we run CUDA programs on modern GPUs. On modern hardware, that's 32 CUDA threads mapping to the same warp. And what I mean by that is, so you can think about if there are a bunch of independent thread contexts here, you can think about them as a bunch of independent contexts sharing the same instruction stream, or you can just think about one instruction stream per context, and you can think about it as one big thing. Two completely equally good ways to think about it. And groups of consecutive threads with consecutive indices in a block, you are guaranteed they will map to the same warp. So you know something about how things are going to get implemented. So a thread block with 256 CUDA threads is mapped to 8 warps, and each SMM is capable of scheduling up to 64 of these warps. So depending on your block size, there might be even multiple blocks interleaved onto the same core at the same time. Yes?
Is 32, is warp defined by having 32 or could it be some number?
NVIDIA could change this in their hardware without you having to recompile a binary. Now, of course, they've broken that by giving you instructions that ask, that vote across a warp and things like that. So the pretty abstraction has been broken. But yes, for many pieces of code, you could not have to recompute the binary, recompile the code to get 64-wide execution or maybe 16-wide execution on a lower end part. Let me talk about one thing so I can end up here in like the next 2 or 3 minutes here. Okay, so here's one more question for you. Imagine I just changed my core. The only thing I did is I said, imagine that there were only 4 warps per machine instead of 64, per core instead of 64. Imagine I wrote a CUDA thread that now this is 256 threads per block, not 128. So I need 8 warps to run this thing. Am I okay? Can I just run 4 warps to completion and then run the next 4 warps to completion after they are done? Just like that trick that we used a second ago. Is this a valid implementation or not of this program? So you're shaking your head no. Why are you shaking your head no? So you're saying that the threads in a thread block can depend on each other. And in this code, where is that major synchronization point? Sync threads. So what would happen if I tried to do that? I would launch threads 0 through 128. They would start running on the machine. They would do their job. They would get to the barrier, and then they would wait. And they would keep waiting. And they would keep waiting. There's one little detail that I haven't told you, is that the GPUs are not built to preempt any of these threads. They're meant to, once you put resources on the core, those threads will run to completion. So they will not yank those threads off, it's hard to yank 32,000 threads off of a processor. It's okay when there's one. It's really hard to yank 32,000 threads off the processor and claim that you're going to get any good performance out of that. So this program will deadlock. And this program will not compile, actually, because it will say, hey, look, you're trying to compile for a GPU with this many threads, and you're requiring that many threads. I cannot run this program. Okay, good. And one last self-check, since this is the end of the day. What about this one? Similar problem. Imagine that I'm trying to build a histogram. And so the kernel is just for every element, take the index, some integer, and increment a counter in an output array, that integer. So let's just say that I have this huge list of integers. I have a histogram of 10 bins, and I just take the integer a sub I and increment that bin. All thread blocks are working on this at the same time. Well, this program deadlock. Different thread blocks are now sharing variables. Is this okay? Is there anything that prevents a scheduler from making up whatever decision it wants to run these thread blocks in any order? Imagine if you were running this on a 1-core GPU. Imagine if you were running it on a 100-core GPU. Are we good? Okay, so maybe you guys should think about, we'll come back and we'll start this with this question. And then one other one is imagine, there's two more things, right? So imagine if, what about this program? I atomic add into this global memory, and then I ask the question, another thread block waits for that value to be 1 and goes. So there's two different things here, two different problems. I want you to tell me which is valid code and which is not.